Okay, now it's 5 after. Last chance. Okay, so yeah. Hello, good morning, everyone. Welcome to Control Club. Today, we got with us Dean Brand from the University of KwaZulu-Natal in South Africa. And he is going to talk about his master's studies that he is about to finish, which is an interesting topic, meaning, as you can see here, title is Markovian Modeling and Calibration of IBMQ Transmon Qubits, which doesn't sound as exciting as it is, I have to say. So please, Dean, take it away.
Sure, thank you. So good morning, everyone. I hope you're all doing well, and thanks for this opportunity to present my work. It's quite exciting to see that it's been received so well. So yes, I'm going to be talking about the work that I've recently done on my master's studies, and we were able to luckily turn into enough for a research article. That is so far just an arXiv preprint, but we are in the process of submitting it for journal publication within the next few months. So to get started, I think it's important to put this all into context by talking about the motivation about why we wanted to do this research in the first place. And it came sort of from seeing the conflicting claims that were out in the literature talking about the IBMQ devices specifically, where IBM were obviously claiming that their devices are very good and very coherent and could do what they were programmed to do. But then there were other research articles coming out talking about the issues with that. We're saying that they are not that well behaved, specifically that they undergo non-Markovian evolution in their qubit dynamics as sort of they were assuming it as a given and then talking about this is the non-Markovian behavior and this is how to actually deal with it. So we couldn't really figure out which one was correct and who was talking truthfully or not. And also we saw that the IBMQ devices provide certain hardware parameters based on their calibration so that you can know the qubit frequencies and the coupling strengths and the temperatures and the coherence times and everything you need to know if you're looking at doing physical simulation on them, specifically in the field of something like open quantum systems, where you could really use those hardware parameters to model a quantum system. But we saw that the way that these values were being calibrated and being extracted were from kind of crude methods that were just going through a very simple single parameter co-fitting on different data sets to find all the different parameters. And we thought that this was sort of they're stepping around a bigger issue that might happen, specifically when talking about neighboring qubits, where two qubits are directly coupled to each other and there's no real mention on how they might influence each other, which we thought might be a bigger issue that they're not considering. So to talk specifically about the qubits that they use superconducting Transmon qubits, which is basically just the artificial two-level system using Cooper pairs in a superconductor, and basically the presence of one or the absence of one represents the binary quantum states. And the Transmon is essentially just that, a quantum harmonic oscillator with a bit of anharmonicity to separate the energy levels so that you don't accidentally drive up to higher energy levels. And the IBM ones specifically, they are modeled using a simple Duffing oscillator Hamiltonian, which is basically just taking into account the qubit frequencies and the coupling strength between them. And for the many different layouts that they have, they all follow essentially the same idea, where there's connected qubits, as in the diagram below, where they have different frequencies and different couplings between them. But we thought that this was also sort of stepping around a problem or ignoring some potential other behaviors, because they only look at the frequency along the z-axis of a Bloch sphere and coupling directly between two qubits. But rather we wanted to extend that to look at the qubit frequencies in all the directions and all axes, and then the same for the coupling strength, to see if they're potentially coupling to other degrees of freedom. And when looking at the calibration data that I mentioned earlier, you can see what I mean, where each qubit is calibrated with different T1 and T2 times, which are the coherence times that I'm going to be talking about mostly, and then their frequencies and things like that. But when they talk about the temperature of the device, it's almost synonymous with superconducting qubits being at very low temperatures and being in these big dilution refrigerators, because that's where superconductivity really becomes useful. But they never actually mention any details about the actual temperature at the time of calibration, and definitely not any actual qubit temperatures, because at a different temperature they undergo different emission naturally through spontaneous emission. And that is modeled through this equation here, which talks about the spontaneous emission as a direct consequence of the qubit temperature. So how many photons get emitted based on how much temperature each qubit has and its frequency. This is specifically where it comes into the theory of open quantum systems, because as I said earlier, they model their parameters through kind of crude, just dark curve fitting methods with a single parameter and then use that. But the actual evolution that these qubits go through, especially in an open environment like being in a quantum device, is a bit more complicated than that, and usually needs the theory of open quantum systems to describe that. And as I mentioned in the beginning, it's usually a battle between Markovian and non-Markovian, because in a Markovian system, that basically just means that it's a lot simpler and a lot easier to model, because it's memoryless. As in, if a qubit undergoes its evolution and it spontaneously emits and decays and loses its coherence, then the energy that it emits is lost to the environment. It doesn't come back and re-influence or re-excite a quantum state, which would be naturally much more complicated to model. And to model the Markovian system, it is almost always through the GK-SL master equation here at the bottom. And what this equation really means is it takes the standard unitary evolution that everyone knows from closed and isolated quantum systems in the interaction picture of how a density matrix representing the system evolves based on Hamiltonian, and then also includes the spontaneous emission that occurs, where most of the terms are quite complicated just because of the derivation involved, but the important ones are these factors of gamma and n, where n is the average photon number that is emitted through the spontaneous emission, and gamma is the dissipation rate, which is essentially the inverse of the coherence time. So it measures just how quickly these decay from a coherent state into a state that we can't really use anymore. And there's some typical benchmarks for how this decay happens, because there's not just one dissipation rate, but rather a few based on the orientation of the qubits and what state it's in. And the simplest one is a relaxation time, which is quite simple. It's the time it takes from an excited qubit to revert back to its ground state. Then there is a T2 time, which is also then has a T2 star, which is just a, it's terms taken mostly from nuclear magnetic resonance and just happens to now be pretty good benchmarks for quantum computing. But these T2 times basically measure when it's in a superposition state, like the plus state, then it measures how quickly it decoheres out of that state and reaches the thermal equilibrium where you can't really extract any more information. And how to do these actually with quantum circuits is nice and simple, really, because for the T1 time, for example, you can just have it in an initialized state and then flip it with an X gate and leave a delay time to see how long it lasts, or after how long will it be at a certain state proportion of being in the ground state or still in the excited state, and then a simple measurement afterwards. For the T2 times, it's a little bit more involved, because specifically for the T2 echo time, as it's known, it basically takes the excited state, rotates it 90 degrees around the y-axis into the superposition state. It's left to decohere, then flipped through 180 degree again, left to decohere some more, and then taken back to its original state. So it goes through a slightly more complicated evolution, but that's mostly to mitigate some external sources of noise. But then obviously the T2 star sequence it's kind of similar, but then it gives a lot more information about what's actually going on. And that effectively just takes the initial state, operates a Hadamard on it to put it into a superposition. It's left a delay, and a Hadamard is applied again to get it back to the original state and then measured. So these three benchmarks are pretty much all that we really need, because they give quite a lot of information on the dynamics of the system and how they decay and which states are more susceptible to noise or to coupling or anything, especially between neighboring qubits. And it gives a chance to then, with bigger sets of 1, 2, or 3 qubits, we can undergo quite a lot of different scenarios. Like, for example, we could have one qubit going through a T1 sequence while its neighbor is going through a T2 star sequence, and then see how those influence each other and give some pretty interesting results. So as an example for what actually happens when I'm talking about the evolution of these qubits, this is an example of experimental data from a single qubit T1 relaxation. And you can see it starts out in the excited state and then undergoes a simple exponential decay into a ground state, where the ground state reflects that. And for a T2 echo kind of sequence, then you can see it starts in the excited state, but then you can see what I mean, where it goes towards the thermal equilibrium, where you can't really extract any more information from the system because every state is equally populated. And as for the T2 star, now you can see why they need a T2 star, because rather than just a T2, because there's a lot more oscillation involved and might give more insight into what's going on, for how fast they oscillate, how quick the decay is, if there's any external noise causing more oscillations towards the end rather than reaching equilibrium, but it's a similar idea. Now, to sort of bring the two ideas together of Markovian master equation and the experimental data for these quantum circuits, we need to look at the numerical solutions to see what would theoretically happen and what's actually happening. And to do this, it's quite a nice feature of the Qiskit SDK from IBM, because they provide the hardware parameters of the devices that we can use as variables in calculations. So it allowed for the use of those variables as the initial conditions for the numerical solution of the master equation. So we can see, okay, if these are the claimed parameters, then what would that lead to in terms of the behavior of the evolution of the system, and then compare that to what's actually happening. And just for interest's sake, I was using the JAX package, which is just very useful for the differentiation, auto differentiation that it has, and the faster compilers, and it's just a very good numerical computing package. So this was used then to numerically integrate the equation and match it to the system. And obviously we saw that the calculations didn't really perfectly match up to the experimental data. But then we could see, okay, which parameters would then end up matching the experimental data, since the claimed calibration data wasn't always perfectly accurate. And to do this, we took the set of initial condition parameters and then put it through an optimization algorithm to tweak those parameters, those dials, to then see which actual values will give a perfect fit between the calculations and the experimental data. And then from there, we could see if it does fit perfectly, then we know it's Markovian behavior and that IBM is still accurate in their claims. Or we could see if it doesn't fit there at all, then we knew there was some non-Markovian evolution going on, which would make sense for the other research that I mentioned in the beginning. And just an example for the optimization algorithm we used the atom optimizer, which is typically used in machine learning models. And as you can see, because of the very quick decrease in error that happens with very few iterations, it's quite an accurate and useful optimizer. So this is an example of a 2-qubit T1 sequence and the data that was then optimized and fitted to the experimental data. And as you can see, it's quite a good and accurate fit. So it's clearly undergoing a Markovian evolution, which is as expected or as hoped for. And yeah, it's quite a good result to get. And similarly for the 2-qubit T2 echo time, then even with more oscillations involved and slightly more complex data, rather than just a simple exponential decay, then the Markovian equations still fit to what we can see happening in the actual devices, with some optimization to get the correct parameters. And then there's another example of just how far this actually can go. As I mentioned earlier, we could put 1 qubit going through a T2 star sequence and its neighbor going through a T1 sequence, and seeing how they influence each other. And it gives quite an interesting pattern of the state population oscillations and changes. But still, even with the Markovian model of the GKSL equation, with some optimization of the parameters, we find that there's an extremely good fit. So definitely no non-Markovian behavior going on, or nothing to really look at other than seeing that what was predicted is true. So I mentioned that we tweaked these parameters and then figured out what are the actual values behind this. And what we found was that we could then extract those and perform our own sort of calibration. And we saw that usually the qubit frequencies were definitely accurate, because that's something that can be quite easily controlled. And the interqubit coupling was usually as claimed, but there were slight sources of external coupling. So it wasn't just directly between the 2 qubits, but it was more useful to have a generalized qubit coupling matrix, which could describe other degrees of freedom along different axes. And most importantly, we figured out that we could use the photon emission to calculate the qubit temperature for each individual qubit. And what we found was that it was along the lines of the claims of IBM that their dilution refrigerators run at about 15 millikelvin. But then what we saw was each qubit definitely does have a difference between each other qubit based on the energy that it has. And the temperature range was usually around between 5 millikelvin, maybe 15, maybe 20 millikelvin, but it was an important value to get, and that might be very useful in actual simulation of physical systems using these qubits. And the most important part of this was that it's a very self-consistent method. So rather than using a bunch of different data sets of the qubit decay times to then do a simple curve fitting to figure out one parameter and then use a whole other data set for a different parameter and so on, like the way that the calibration is usually done, this gives a way of running an experiment and then getting every single parameter from that and seeing how they influence each other and how they might behave together. What else we found with this is that if we were to scale this kind of a system, we wanted to see if this could work with single qubit, 2 qubit, or 3 qubit systems to see how easy it is to perform this as a sort of quantum process tomography. But naturally, we knew that the qubit sizes, qubit numbers in these devices are growing rapidly. Like now we're on the scale of a few hundred qubits, and in the next few years, it's going to scale up to a few thousand qubits. And with the numerical modeling for the GKSR master equation, it's very difficult to model a big system because it grows exponentially in the dimension of the quantum system with the density matrix. So we can't have a 1,000 qubit system because we'll have a density matrix of 2 to the 1,000 dimensions. So we wanted to see if the 2 qubit version of this experiment would give different results to doing with 3 qubits, let's say, even if it's the same subset. And luckily what we found was that if we did it with a 1 qubit, 2 qubit, or 3 qubits, the results were exactly the same. But specifically, we looked at the 2 qubits because that's the first one where we could look at the interqubit coupling. And seeing that if we take 2 pairs of qubits and sort of overlap them, like do an experiment on qubit 0 and qubit 1 and qubit 1 and qubit 2, even though it's both using qubit 1, how does that compare to using all 3 of those qubits in the same experiment in just a larger subset? And what we found was that the results are pretty much exactly the same. You can get the same values and the same precision using a much, much smaller system. So as an alternate to trying to model a 1,000 qubit system with an incredibly big numerical model, we found that it's much, much more ideal to rather stitch together all of the 2 qubit systems with the overlapping qubits. So we can find each parameter for each qubit and then all the coupling strengths in between them. So for looking for doing this as a calibration method or quantum process tomography for much bigger systems, then that's obviously the recommended route to go, is to do the 2 qubit pairs each time. And especially because, as you can see here, for the 3 qubit version, it's still quite accurate and followed the ideal evolution, but there are some slight differences in each different state just because of how the measurements happen and how difficult it is to actually get all of this data from the sets, because you have to recreate the quantum circuit each time and just hope that each system scales as it's supposed to be, as if we could watch it continuously. But the slight deviations for each little thing add up to be quite a lot. And we didn't try a 4 qubit system because we already knew that the data would be very, very inconsistent and very difficult to reproduce. So we saw that using just the 2 qubit groupings is much more efficient, and doing that over each pair like that, we could then see the necessary information without sacrificing any precision or accuracy, just based on the difficulty associated with a bigger system. So those were the main findings of this paper, was that we could extract the parameters, the hardware parameters of the devices through quite simple experiments and a little bit of numerical optimization to have a fully self-consistent method of calibrating the device and extracting the necessary parameters, while also proving that, at least for these simple benchmarks of just a few qubit gates deep, maybe, that the qubits are definitely undergoing Markovian behavior, which is ideal because it's much, much, much easier to model and to predict what's going on in the system. So for the other papers that I mentioned where they found that there was non-Markovianity going on and that they proposed all these other methods to deal with it, that might be applicable for much bigger systems, but at least we know for the hardware parameters that are given in the calibration of these devices, they are reliable, but can still be improved with this version of state process tomography, which is also not too difficult to implement and could even be something that is one day implemented into the software development kit to run through your own calibration quickly at the beginning of an experiment or program to know fully exactly what's going on with these hardware parameters. And yes, we are hoping to add one or two more considerations for this, like the pure dephasing channel or things like that, just to see if there's any more slight tweaks that we can do before sending this to publication and then continuing to work on the same topic down the line. And that's it for the summary of the work in the paper. There's a lot more details in the paper, so I hope that that goes well, but yeah, that's it. So if there's any questions, I'd be happy to give it a go.
Thanks a lot. Yeah, so questions from the audience? Anyone? Please just go ahead. Shai has his hand. Yeah.
Yeah. So first, I like the approach because it's very much similar to the approaches we take. You know, you always like when people do something that's similar to things you're doing because it makes you think you're smart. But I have an issue with the results, and the issue is that, you know, it's well known that superconducting qubits mostly have 1/f noise.
Mm-hmm.
And I put in the chat a paper from Lidar from 2018, where he took the IBM 5-qubit system and showed that he can do dynamical decoupling and significantly improve, you know, T2 times. And I'm finding it hard to, you know, figure out how these two results live together. And there are other, you know, there are multiple claims of non-Markovian behavior in superconducting qubits. So I'm confused. I understand what you did. The fits look like they work very well. So what am I missing here?
Yeah, I'm also not really sure where exactly they fit in together, because I think that might be something to look into for further research. But for what we've done in this paper was just look at the basics of seeing what happens and can we model to it. And yes, then obviously down the line to look at what other influences there might be, like you mentioned, the 1/f noise and things like that.
Yeah.
But yeah, so that was out of the scope of the research in this paper, but definitely worth something worth looking into.
Okay. So let me maybe ask this question in a different way. Have you tried in simulation creating non-Markovian noise and seeing how that would appear in the experiments and measurements you do?
No, we haven't tried that, because yeah, that would be a good thing to consider. But our approach to this was a much simpler idea of our categorization of non-Markovianity just being anything that doesn't fit to the Markovian model, to see if there's any, because I've seen in other papers where they talk about non-Markovianity, it's usually a slight bump back in to disrupt the exponential decay or something like that. But what we saw here was the models fit quite well. So at least in this more simplistic idea of it, it did fit the definition.
Right. So I can say, like, from a position of, you know, if I were to review a paper like this, I would kind of ask you to explain those other papers and one can come up with probably 5 or 10 with less than an hour of googling, because something doesn't compute, and I can't put my finger on it, because I don't see immediately anything wrong in the way you went about doing the experiments you did, but yet kind of I get 1 + 1 = 3, and I'm not exactly sure what to do with that.
Yeah, I understand what you mean, because we know that this was quite a simplistic approach just to see the basic idea of what's out there, because we saw that there wasn't really much in the literature covering this kind of approach, but we know there are a lot more
so
factors that we should include in.
One way that might explain it is that, kind of generally speaking, what the model that you see in the system is very dependent on how you drive it, right? Just let's take 2 coupled harmonic oscillators that have different frequency. If you're not, if you're driving system A far away from the frequency of system B, you'll basically be completely unaware that system B exists. And so the way people usually get, for example, the power spectrum is not just doing, Rabi-Ramsey or Ramsey echoes, but they actually do dynamical decoupling sequences and see how the results differ as a result of the details of the decoupling sequence. And it might be, and that's why I asked if you've run this experiments with a simulation of non-Markovian noise. I've never done this myself, but somehow I have a hunch that if you have non-Markovian noise, but you run experiments designed to get Markovian parameters, you'll still get a good fit to Markovian behavior. Because it's somehow, you're not driving the system in the relevant frequencies, let's say, that would be the analogy. To see, if you have, let's say, leakage levels and it's unharmonic, right? So if you're kind of narrow enough spectrally, you're not even aware that there's a leakage level. But if you're wide spectrally or you're driving at some different parameters, suddenly you escape into the leakage space. So how you drive the system is very, very important in which effective model of the system you're seeing. So my hunch would be to double check that, because something doesn't add up.
Yes, yeah, that's a good point. Thank you. I'll definitely mention that with my co-authors and see if we can look into something like that. Because I know especially a very frustrating part of this experiment was the limitations of the backend of trying to use what IBM will actually give us to use. So it's much harder than, for example, actually having access to your own quantum computer and being able to take into account all those parameters. But obviously, the things that you mentioned definitely can be implemented even on the IBM system, and I think we'll definitely look into that.
Okay, so here we might be able to help. We have, not this month because the fridge is down, but generally speaking, we have several superconducting chips at Jülich. We built a Qiskit backend for them, meaning you can take general Qiskit circuits, including Qiskit pulse, and just execute them on the machine. And we have a job queue and everything. It behaves exactly like an IBM cloud stuff. So you could take your, we give you access to the VPN. You can run your experiments on our machine with just changing like 2 lines of code. So if this is something that looks interesting for you, we can discuss this further. But this is certainly something we can do.
Yeah, thank you. That is a very...
Machines are designed to be publicly, well, not publicly accessible, but kind of accessible to collaborators and stuff. So,
yeah, thank you. I'll definitely mention that with my co-authors and then see what avenue you want to take going forward. But yes, that is very nice, Alpha. Thank you.
Right. Thank you.
Yeah, obviously we had that in mind because we are doing very similar work from a conceptual level. That's why we're also very interested in the talk. So I might have a question that's more, yeah, methodological. That is, so you showed the, you did these experiments with the 1, the 2, and the 3 qubit with the plaquetting, right? Where you look at if the behavior is consistent. And I wanted to clarify, so are you using the exact same model for in all cases? Do you try to refine the model in between? Or maybe can you just re-explain how you go about that?
Sure. So for this talk about consistency in across the different sizes, it was more just for the simple case of seeing if we can run the exact same quantum circuit and fit it in the same way to the same equation, but just with different dimensions, obviously, by including another qubit and extending the density matrix, and then seeing if that changing as little as possible between those still gives the same results, or if there's anything strange happening where 2 qubits behave very differently from 3 or anything like that.
Okay, thanks. So I'm sure that I'm understanding correctly. So it's the same model parameters in each case.
Yes.
Okay, thank you. More questions from the audience? Just go ahead.
Yeah, maybe I just wanted to ask, so these, let's say these points in these plots are, let's say, the same queue of jobs being run, or does the IBMQ machine get reset and recalibrated after, let's say, some runs that could somehow destroy some Markovian noise, even though the time scale, as Shai said, should suggest that someone already sees some non-Markovianity here.
Yeah, so we try to be as careful of that as possible, where for each experimental run, we'd run it all as one job altogether to get all of these data points. That's why there's 75 data points, because that's the maximum that NISQ would allow for. And we did it with as many shots as possible to get minimize error as much as we could. But yes, each plot does correspond to a different job, but we also did make sure to take into account their calibration timescale, because we know that at least based on the calibration data they give on the website, is they calibrate every roughly 1 or 2 hours. So we did these jobs, we try to put them in as closely queued as possible so that we can minimize that. But like I said, that was one of the limitations of using the IBM devices, was that we ran the risk of maybe running one job and then another job from somewhere else would come into the queue and maybe influence the device in whichever way, and then influence the results of the next job that we had in the queue. But we try to mitigate that by just running this over as many times as we could and seeing if there are any inconsistencies in the results. And we saw that this was a pretty good outcome.
Okay, so even, let's say, if the job was run after almost 2 hours since the previous recalibration, you couldn't see any inconsistency, let's say.
Yes, because I also made sure to try at different times to see as soon as possible after it was calibrated, or even then after 1 or 2 hours after it's calibrated, and certain points through that to see if that has any effect on it. And there wasn't really anything major that we could see. So because we wanted the idea of that we could run this at any time and it would work as claimed. And we wanted to see if there were any caveats to that, to see this can only be run at a certain time in the calibration or whatever. But the reassuring result was that whenever we run this, it gives decently consistent results.
Yeah, makes sense. Thanks.
Sure.
All right. More questions?
Yeah, I have just a curiosity. Do you know if in Qiskit the rectangular passes that use in the sequence are really rectangular or are more shaped like the Blackman pass or Cauchy pass?
I'm not actually sure. I don't think we looked into those details. That's sort of beyond my knowledge of Qiskit.
Okay, yeah. Yes. No, because I mean, I guess if you use really a rectangular path, maybe you can drive your system with very high frequency components, and maybe this could also affect the Markovianity that you see on your results. That's a point. I mean, it's quite linked to what Shai said before.
Yes, we did at one stage want to look into designing our own pulses for these different gates using Qiskit Pulse to have control over whether it was rectangular or Gaussian or whichever shape we wanted, but that proved to be a lot more difficult and limited by the interaction that the front end wants to provide. So we then went back to the idea of anyone should be able to use this in the just by importing Qiskit and then running this without extra consideration for whichever pulse system they want to use, and just leave it there until we could get access to a system or hopefully encourage someone else to use a system where they have more control to see if that's a possibility.
Okay, thanks.
Yeah, okay. If there's any more questions, go ahead. Okay, otherwise I might have a more detailed question that is, so what actually is the goal function that you're using to match the model to the data that I'd be interested in?
So do you mean in the optimization, like the cost?
Yes, so you're doing an Adam optimization, right, where you try to fit the master equation simulation to the data. And I mean, we struggled with similar things, so I would be interested in, so what are you using to compare? Do you straight up compare the distance of the points?
Yes, it was just a very simple least squares kind of regression. We started with that and then didn't really see a need to have any more complex.
Right, approach. Nice. But that in itself is, I think, a statement that the system is very well behaved. Yes, I would say, because if that works, yeah, cool. I'm just gonna have another detailed question. If other people want something, please just jump in. And that is, so in the modeling, you showed this Hamiltonian with the 3D Pauli basis, right? Where you explained also that maybe the axes are not exactly aligned the way that you expect them. Yeah, if you could go there. Did you try to quantify how non-diagonal this is? So looking at this, I would think, so can you simultaneously diagonalize the two qubit Hamiltonians and the coupling to get some effective like Z thing? Did you look into that?
I did, yes, and I tried a few different methods because I wasn't sure which exactly would give the best sort of projection onto the Z-axis to take either the norm of the vector or a few different methods like that. And what we found was that any deviations to the simpler Hamiltonian that IBM uses and that they provide as their claim, the deviations were very slight and wouldn't really reflect in any kind of diagonalization like that. So it would be, if we were going to look at what deviations there were, it's much easier to see if it's just kept in this full matrix form and then see the slight deviations along each of those axes. if I understood the question correctly.
Yes, exactly. So I was thinking, I mean, also we probably need to think about, so if the readout basis corresponds exactly to one of these, or so what you're actually seeing. But this is interesting because I haven't seen this detail of trying to think about yeah, coupling axes, probably some dipole moments that go on in there.
Yeah, it was
right?
mostly just to see if there's anything sort of hidden along the different axes, any extreme couplings or something like that, or maybe a frequency that's along the x-axis that no one really thought about, or anything like that. But what we saw was, okay, it's pretty much accurate, and there's only slight deviations that wouldn't really come into play. But if they were, then we've got the method to see them.
Nice. That's also reassuring, though.
Yes.
But with the whole story of calibrating these things is, we might turn out to see these things prop up when we would get to really higher fidelities in the system. Then these, as you said, like slight deviations might become more visible, right? If the accuracy with which we control these systems becomes higher, then all kinds of weird things like that might show up. So it's nice to have already, have that in mind.
Yeah, this is a slightly better approach than the simpler model.
Okay, thanks. So that's all I have. So anyone came up with a question in the meantime, please speak now. Otherwise, I think we'll close the seminar. Okay, if that's not the case, then yeah, thank you again for taking the time to explain this to us. It's very nice. And as Shai mentioned, we might be interested in collaborating further on this. As I said, we're thinking about similar things, and specifically the problems that you explained around the access to the IBMQ machines could be resolved by having basically a private cloud like that, right? So yeah,
yes,
I guess we'll be in touch after this maybe. And yeah, so also thanks to everyone else for showing up, participating. So yeah, let's see each other next time. Bye.
Thank you. Bye.
Bye for now. Thank you.
Thank you.